Hello everyone, today let's take a look at Quantipus number 37. I know it says 34, but it should say 37, and it's basically asking us how many terms are there in the expansion of A, this one right here, B, x plus y to the 6, and C, x plus y to the n. So getting into some binomiality here. So for part A, I just drew it out again here. Obviously, we're not going to want to count them all manually. We're going to want to find some type of easier way to count the number of terms. So what would some example terms look like? Well, if I take A and then multiply by D, and then I could have P and then X, for instance, if I just take the first one from all of these. And then also we're going to have AE, PX, that's going to be another one of our terms. And then we're going to have AF, PX, and etc. Now we may also have BFPX, and then these terms are all going to be added up. And notice that each term is of length 4 because we have 4 of these up here. So this is actually a really simple problem because every single one of these is unique. We can just say, okay, we're choosing from our first term any of 3, and then from our second one, we're choosing any of 3 as well. From our third one, we have 4 terms, so we're choosing any of 4, and then for our fifth one, we're choosing any of 5. So what are the total number of terms? Well, let's just multiply all these numbers, 3 times 3 times 4 times 5, and when we do that, we're going to get 9 times 20, which is going to be 180. So that's the answer for part A. Now let's come down and look at part B, where we're calculating the number of terms in x plus y to the 6th. So this is what it's going to look like all expanded out, and notice that the terms in here are not all unique like they were in part A. So essentially I have any of 2 choices from this one, any of 2 from this one, and any of 2 from 6 of them. So it's going to be 2 to the 6 choices. But notice that all of these terms are not going to be unique. For instance, if I select an x first here and then an x here, I'm going to get x squared, and then maybe I select 4 y's from the remaining 4. So I have x squared times y to the 4th, but that's just going to be exactly the same as if, for instance, we selected 4 y's here, and then an x here, which would also give us x squared times y to the 4th. These are the same terms. So essentially, because these terms are not all unique, when we do this, we're going to be overcounting. So it's asking us for the number of terms in the final expression. We know that when we add all this together after we expand it, right, we're going to end up with some coefficient here, and then we're going to have x squared y to the 4th. So this is all going to be one term. So now how many unique terms are we going to end up with? Well, we could have this term with some coefficient x cubed, y cubed, or we could have x to the 4th, y squared, or we could have x squared, y to the 4th. So essentially what this is saying is the number of ways to distribute 6 units of powers, right? All these terms have powers that add up to 6, right? 3 plus 3, 4 plus 2, 2 plus 4. So let's just choose one of our variables. Let's say x. What are the units of power that we could give it? Well, we could give it 0 if we select all y's, and then we'd have y to the 6th. And we could give it anything up all the way till x to the 6th, where we select all x's. So x's power can take any integer between 0 and 6. How many integers are there between 0 and 6? Well, there's going to be 7, obviously, so that is our final answer. Now, when we move on to part C, it's going to be pretty similar argument. We have x plus y to the n. We want to count the number of terms. So we're just essentially multiplying x plus y n times, obviously. So it's going to be the exact same argument as in part B. You know x can take any power, let's say n minus k, where k is in the range of 0 all the way up to n. And then whatever value we choose for this x, there's only going to be one value for y, and it's going to be k. So this value right here is predetermined based on what we choose for k. Now, how many different ways are there to choose k? Well, it just goes from 0 to n integers, so we have n plus 1. Just to go over some examples, if we choose k to be 0, then we have x to the n term. That's what we're counting. If we choose k to be 1, then we're counting the x n minus 1 times y to the 1 term. And if we choose k to be n, then we're counting the x to the 0, y to the n term, right? So we're going to be counting every possible combination here. So the final answer for part C, the number of terms in here, is just going to be n plus 1.